Okay, so connecting with the previous lecture, in the last lecture I have discussed one-way ANOVA. Now the today topic is the two-way ANOVA. In two-way ANOVA, we will handle two independent variable and there will be one dependent variable. But in two-way ANOVA, there are two different cases. One case will be without interaction and one will be with interaction, or one will be without replication and one will be with replication. So I'm just going to discuss that what is without replication and what is with replication. So starting from the two-way ANOVA, two-way ANOVA is applied to a situation in which you have two independent variable and one dependent variable. So as you remember, in the last lecture we discussed one-way ANOVA. In one-way ANOVA we have only one dependent variable and one dependent variable, and we check the performance, we check the behavior of those two variables, their impact on one another. So in two-way ANOVA, we will basically handle two independent variables. I will also discuss some example before going to start some practical example. Each of the independent variable may have any number of levels or condition. For example, treatment 1, treatment 2, treatment 3, no treatment. Okay, so basically in each independent variable, maybe there are some more categories. For example, in first independent variable, good, bad or worse, these are three different categories. Okay, so we will further disaggregate, we will further calculate, we will further check their effect on the dependent variable. In a two-way ANOVA, you will obtain two F ratios. So definitely, because in one-way ANOVA, we have only obtained one F ratio because that was a comparison of one dependent and one independent variable. Now we have two independent variable and one dependent variable. So in the first instance, we will check the behavior of the first independent variable with the dependent variable, the impact of first independent variable on the dependent variable, and the second F ratio will show us the effect of second independent variable on the first dependent variable. One of these will tell you if your first independent variable has a significant main effect on the dependent variable. So this will be basically F1. Second will tell you if your second independent variable has a significant main effect on the dependent variable. So in order to further clarify the meaning of two-way ANOVA, let us consider a simple example. Let's suppose what is the impact of gender, ethnicity and their interaction on annual income. Okay, so now annual income is what? This is dependent variable, and gender and ethnicity are independent because gender have no connection with the ethnicity. Male, female have no impact dependency on ethnicity, but this have some dependency on the annual income. One of these will tell you if your first independent variable has a significant main effect on the dependent variable. What is the main effect of gender on income? Let's suppose this is independent variable and this is dependent variable. So what is the main effect of gender on income? Regardless of across all level of ethnicity. So this is mean considering one independent variable effect on the dependent variable, which in this question is income. A second will tell you if your second independent variable has a significant main effect on the dependent variable. What is the main effect of ethnicity on income regardless of across all level of gender? So basically in this example, I hope that you understand that now we have two independent variable and we want to check their effect on the dependent variable. In this case, the dependent variable is the income. With the two-factor ANOVA, we can not only see the basic result from both of these factors, but we can examine how the two factors interact with each other. Okay, so basically we want to check that how they interact with one another. Okay, so just like in one-way ANOVA, we construct the null hypothesis. So similarly, now we are dealing two independent variables. So therefore, our hypothesis number will also be increased. Maybe in the column you have one consignment and maybe in the row you have another observer. So how we will construct the null hypothesis? For example, all the column consignment mean are equal. Let's suppose in the column we have different consignment, different mean. Let's suppose gender, ethnicity, etc., etc. So all the column, the mean of all the salaries of gender and ethnicity are equal. Let's suppose H1 will be the alternative. Not all mean will be equal. At least one will be greater than. Let's suppose. Now all the rows observer mean are equal. So soon I will discuss a simple example. Let's suppose in the rows there are different mean cattle, different type of kettles. In the column, let's suppose we have different type of rations. So mean all the kettles mean are equal, not all the row mean are equal. So allow two different treatment to examine simultaneously. So basically in 2ANOVA we are going to conduct an analysis in which we want to examine both independent behavior simultaneously. So from this example you will further understand that we have two factors in this one. One is marketing strategy. So you can see this is marketing strategy. In the column, in marketing strategies, there are further treatment, convenience, quality, price. So these are further disaggregation of the marketing strategy. In the column, in the rows, the factor B is advertising media. So in advertisement media, we have some print media and we have some electronic media, TV and newspaper. And convenience, quality, price are the sub branches of marketing strategy, and TV, newspaper are the advertising media. And dependent variable is sale. So CT1 sales, CT2 sales, CT3 sales. Similarly in all cities, so sale in this case is your dependent variable, and marketing strategy and advertising media are your independent variable. Now we want to check. Now we want to further construct an analysis to check their behavior, their effect on the sale. What kind of effect it have? So how we will construct different alternatives in this question, I want to show you that convenience mean, because we want to check marketing strategy, the alternative hypothesis, convenience mean, quality mean and price mean are equal. They have same impact on the sale. Similarly, the alternative hypothesis of this will be that all the mean are not equal for convenience, quality and price. Similarly, for the advertising media, the null hypothesis will be the mean of the TV advertisement and the mean of newspaper advertisement are same. And the alternative will be mean and TV advertisement mean are not same. So at this way you will interpret the null and alternative hypothesis. So in 2ANOVA, as I already mentioned, there are two types of categories. One is without replication or without interaction. In some books, in some research paper, they call it without interaction. Mean, for example, in the last question, marketing strategy and advertising media impact on the sale, but it's mean they individually check the impact marketing on sale, marketing on convenience on sale, quality on sale. But when we going to construct an analysis where we want to interact the impact of this at the same time and impact of this on this at the same time, so this will be with interaction or with replication. So this is also known as randomized block design, RBD. So randomized block design, why it is called randomized block design, I will discuss this very soon. In randomized block design, there is one factor or variable that is of primary interest. However, there are also several other nuisance factors. So that is why it's called block design, because we will freeze some block, which is also called nuisance factor. Those factors have not direct impact on the analysis, direct impact on the dependent variable. So nuisance factor are those that may affect the measured result but are not of primary interest. These are not primary interest, so we want to reduce their impact for the time being. The way to control nuisance factor is by blocking them to reduce or eliminate the contribution to experimental error contributed by the nuisance factor. Blocking variable is second treatment variable that when included in ANOVA analysis will have the effect of reducing the error sum of squares. So basically when we block these nuisance factor, these primary which have not primary of interest, so we reduce their effect by reducing the error sum of square term. So 2ANOVA without replication, a two-factor randomized complete block design is complete balanced two-factor design in which the effect of one factor, the treatment factor, are of interest. So let's suppose in the previous example, the media, the print media, the newspaper and TV are of interest, while the effect of other factor, let's suppose in the blocks there was convenience, quality and the other thing are not of interest, let's suppose. So the blocking factor is included to reduce the uncertainty in the main effect estimate of the treatment factor. A two-way analysis variance is used to estimate effect and to perform the hypothesis test on the main effect of the treatment factor. So basically we want to converge the process into one specific point where our main interest line. We will reduce the impact of those nuisance factors which are not primary interest. which are not have direct interest. So a randomized complete design provide a great advantage when the blocking factor strongly affect the response and provide a relatively small disadvantage when the blocking factor has little or no effect. So basically this is just a general structure. These are the treatment and these are the blocks. So we just want to study this from one side. We don't want to interact this with this, this with this, treatment 1 with this, treatment 1 with this, but we just compare this these whole treatment with this whole as a whole. We not individually consulting each individual with this individual with this. So this is called without interaction. We don't want to check the interaction between each and every factor. We just want to conduct an analysis, a journal analysis, a journal interaction. Okay, so I hope that you understand. But before going to that, I just want to discuss a very simple example in order to further clarify the meaning of two-way ANOVA without replication or without interaction. For example, we have 4 breeds of cattle, B1, B2, B3 and B4. So these are different breeds of the cattle were fed on 3 different rations, and they are basically fed 3 different rations. Okay, gain in weight, and now they want to check the impact of these ration on these breed, their weight. That what kind of effect these different ration have on their weight. Gain in weight in pound over a given period were recorded as given below. So you can see these are the different breed. Let's suppose this is breed 1 from, let's suppose, from Punjab. This is breed 2, let's suppose, from Balochistan. This is breed 3, let's suppose, from KPK, and this is breed 4, let's suppose, from Sindh. And they basically, these are different breeds, and they want to feed with different rations, and then they want to check their weight. That is, this specific rations have an impact on the weight of this breed and this. Okay, so we want to check now while using without interaction or without replication approach. So level of significance, we want to use a 5% level of significance. So they want to check there are no difference in the main gain in weight for the different breeds. So now we want at the first instance that there are no difference in the breed weight. All the breed mean weight are same. Okay, so this is our first. This have no interaction with the rations, but this is there are no difference in the mean gain of weight. So we want to breed and the weight. There is no interaction with the rations. We just want to check the impact of breed and their weight. And the alternative will be there are no difference, so there are difference in the main gains and weight for the different breed. The second one is there is no differences between rations. So mean all the ration who you are feeding to the 4 type of breeds, they have same mean. So now you can, I hope that you understand that we not doing an interaction between R1 and B1, but we doing an interaction with R1 with weight, R2 with weight, R3 with weight, and breed with weight, B3 with weight. So we are not doing a interaction. So that is why it is called without replication. Without interaction, we not interacting B1 with R1, we not interacting B2 with R2. So when you conducting an interaction, that will be called two-way ANOVA with replication or with interaction. So basically in this question, the main objective that I am not going to do an interaction. I just want to do an analysis without interaction. So for this question, how do you construct null and alternative hypothesis? All the column breed means are equal. So all the column breeds mean are equal. All these weights, so there are no difference in the main gain and weight. So the no difference mean all the mean will be equal. Alternative will be no. All the column breeds mean are not equal. There is some differences. There is some differences in the mean of the weight. Okay. All the rows. So now at the first instant, we want to compare this independent variable. Breed is an independent variable. These 4 type of breed are totally independent. So we want to conduct an analysis with the dependent and independent. Independent, this is now another independent, and this is dependent. Weight is dependent. So all the row different ration mean are equal. So mu R1 is equal to mu R2 is equal to mu R3. Not all the row different rations mean are equal. So I hope that you understand what is with interaction and what is without interaction, or without replication or with replication. So further, we will take the same question we want to solve this now. It's a little bit different from the one-way ANOVA because but some specific terms and conditions are very similar. So I will discuss this, that how you will calculate, how you will construct total sum of square, error sum of square, the correction factor, etc., etc. So you can see these are our given breed: 46.5, 62, 41, 45. So 46.5, 62, 41 and 45. I just did this calculation, and these are the ration. So what we will do, we now want to calculate n. What will be the n? What will be the number of observation? So you can directly calculate it from this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So our observation are 12. Or if you want to use this formulation, n is equal to C into R. So how many columns we have? We have 1, 2, 3, 4. And how many rows we have? 1, 2, 3. So 4 into 3, column into rows, 4 into 3, 12. Or you can directly count it. You can directly count it from this in order to calculate n. Now, in order to calculate correction factor, as I already discussed in the one-way ANOVA, so the correction formula is much similar, is the same, and we denote it with g square by n. So how we will calculate g? So you know the sum, we call it bj, okay, because the column are representing breed, different type of breed. So add this one, so this is b1, this is b2, this is b3, and this is b4. When you add all these, because in one-way ANOVA I call it tj. So basically this is the sum of tj, 144 plus 143 plus 88.5 plus 105, it will be 481. And similarly, if you add this row, we will also conduct an analysis for rows. 46.5 plus 62 plus 41 plus 45, it will be 194.5. 47.5 plus 41.5 plus 22 plus 31.5 will be equal to 142.5. 50 plus 40 plus 25.5 plus 28.5 is equal to 144. So if you add this, and if you add this, and this one, the sum will be 481. This is basically the column sum and the row sum will be equal. So this is 481. So now we need this g value in the correction factor. You need to put this 481 square divided by n. So our n is 12. So 19280.08 is your correction factor. Now the total sum of square formula is much similar as we already conducted in the one-way ANOVA, one-way analysis of variance. What you will do, you will take the square of this. So 46.5 square is this, 47.5 square is this, and 50 square is this one. Similarly, 62 square is this, 41.5 square is 172, 2.25, 40 square is this one, 41 square. So what you will do, in the next column, we need to sum it. We need to sum this. So the sum of this is, you can see, this is x1 square. Let's suppose this is x1 square. Okay, this is x2 square. This is the sum of this one, and this is the sum of this, and basically this is the sum of this one. So when you add it, you will get 2072. This will be double summation. So that is why I use I and j. Double summation x square ij minus correction factor. So this is the same formula as we already discussed in one-way ANOVA. So this will be 20729.5 minus CF is 19280.08. So this is 1449.42. Now we want to calculate, because we have two independent variables. Before we use treatment sum of square. Now we will use another term which is called column sum of square, because we have two independent variables. One is breed, different type of cattle, and we have different type of rations. Cattle are representing in the column, so that is why we use column sum of square. Column sum of square means summation b square j. So you remember we use summation t square j. So basically this is the column sum of square. So what you will do, this is basically the square of 144 square is this one, 143.5 square is this one, 88.5 square is this one, and 105 square is this one. When you add this this and this is called summation b square j, and summation b square j is 60185.5. So that is why this is 60185.5 divided by r. This is the formula. So how many rations we have? We have 3 rations minus correction factor. So this is 781.75. Now we also want to conduct for the rations for the another independent variable. Another independent variable are presenting in the rations and they are presenting in the rows. So row sum of square. So row sum of square, because we have already calculated r square ri. Now you need to take square of this. So the square of this is r square I. The square of this is 20306.25. So this is the square of this. 144 square is this one. When you add this, this will be equal to summation r square I. So summation r square I is 78872.5 divided by column, because we now comparing column with rows. So row sum of square formula will be C. The column sum of square we will divide with R, and row you need to divide with the number of columns. So we have 4 column minus correction factor, which is this one. So this is 438.04. Now we need to calculate error sum of square. So you remember in one-way ANOVA we use total sum of square minus treatment sum of square. But now the formula is changed, because in that case we have only one independent variable and we denote that independent variable with the treatment sum of square. But now we have 2 independent variables, one is in the row and one is in the column. So total sum of square minus row sum of square minus column sum of square. So total sum of square is 1449.42 minus row sum of square is this 1438. So we just write, and column sum of square which is 78. So which is 781.75. So basically this is our error sum of square. This is also called within sum of square. You remember within. Okay. So now we need to construct an ANOVA table. In ANOVA table we need to construct now, because this is also a little bit changed. These two are between and the error one is we call it within. So between rows. So degree of freedom for rows will be, how many rows we have? We have 3. So 3 minus 1. So it will be 2 degree of freedom. Column, how many column we have? 1, 2, 1. This is 1, 2, 3, 4. So 4 minus 1 is equal to 3. Okay. And what is the formula for error within? You need to remember this formula, which is r minus 1, r minus 1, row minus 1 and column minus 1. So r minus 1 you already did this one. R minus 1, so we have 3 rows, 1 minus 1. We have 4 columns, so 3 into 2 is 6. Or if you want to put these values, so 3 into 2 will be 6. When you add this 6 plus 3, 9, 9 plus 2, 11. So this is RC minus 1. Or this is also equal to n minus 1. N is 12 minus 1, so it will be 11. Now the second column is as usual is like the one-way ANOVA sum of square. So between rows, so row sum of square was 438.0 for this one. And column sum, between column we have already calculated sum of square for column, which is 781.75, and we have also calculated within, which is also called error sum of square, which is 229.63. Now in the next column we need to calculate average. How you will calculate average? This divided by their degree of freedom, so it will be equal to 219. This divided by their degree of freedom, so it will be 260.5. And this divided by this degree of freedom, error degree of freedom, 38 points. So as I already mentioned, in 2-way ANOVA we will construct 2 F ratios. So first F ratio will be between rows, which will be, first ratio will be, because I already mentioned the first ratio will be not all the column breeds mean are equal. We want to check this now. So between rows, because breeds are mentioned in the rows, all the mean of the breed will be equal. So in order to calculate this between rows mean square, this divided by the error. So 219.02 divided by 38.2716, it will be equal to 5.723. The second one is the row independent variable. So between column mean sum square. So between column mean sum square is 260 divided by error sum of square, which is 38.27. So this is 6.80. Now we have already calculated this is F1 and this is F2. Now we need to construct a critical region. So for F1, because this will be this is f, which will be started from 0, and we want to check it on 0.05. so these degree are 2 degree of freedom. So f1 is for which degree of freedom? For the breeds. So basically these are the, this is for the rows, the rations. This is for the rows versus ratio with error. So this is the row degree of freedom is 2 and the error degree of freedom is 6. So 2, 6. So once again I am going to the table to calculate this value for 0.05 and 2. So you can see this is our F table. We are looking for 0.05. Our numerator degree of freedom is, which is basically for the row. So this is 2 and denominator degree of freedom is 6. So you can see this is 5.14. You can see this 5.14. So we will write this 5.14 in the figure. So we just write this 5.14. Now we will check this is the calculated value of F1, which is mean F1 showing the rows comparison with the treatment with the error. So we will consider that F critical value, F statistic value, which is 5.723. So we have calculated the tabulated value of F, which is 5.14, and this is threshold boundary of accepted region and this is rejected region. So 5.72 will be lying in this rejected region. So as calculated value of F1 5.72 lies in the rejected region, so we will reject H0. Similarly for F2, F2 mean basically is the column sum of square, mean square, which is 260 divided by the error, which is 38, which is the calculated value of F is 6.80. And while calculating the F statistic value from the table, so F 0.05, and why we change this degree of freedom? Because it was 26, because this was for the row degree of freedom and the error. Now this is column degree of freedom, which is 3, and this is 6, so 3, 6. Now it is 4.76. So as the calculated value of F2 6.80 lying, so mean this value is much higher than 4.76. So that is why we will also reject H0. So in both cases we reject H0. H0 mean that all the mean of the breed and their impact on the weight, their weight average is not equal. So this one is correct. And all the rows different mean are not equal. So that is why we already proved this. Our null and alternative hypothesis, both one are rejected. Alternative hypothesis accepted. Thank you.